So we're here with Jim Hogg. You're a program manager, architect on Visual C++ compiler.
Program manager on Phoenix backend, yes.
Phoenix backend. So let's talk about Phoenix. What is Phoenix?
So Phoenix is a project that's been underway for, I guess, coming on about 4 years now.
Okay.
And the idea is that we will build a framework, that's to say a large collection of OO classes, a framework that can be used for building compilers and software analysis tools.
Okay.
So I guess the analog would be if you were going to build an application, you would use the .NET framework.
Mm-hmm.
But if you were going to build a compiler, you'd look somewhere else, and in fact you'd look to Phoenix. So it's analogous to the .NET framework, but for the specialized case of building compilers and software tools.
So an example of I might want to build my own .NET language. If I need a compiler,
Right.
I would use Phoenix. Is that what you're saying?
Nearly.
Nearly.
So
I'm always nearly correct.
So compilers break into two parts essentially, which we call a front end and a back end. Right?
Okay.
So the front end is the chunk of software that takes the source language, so it could be C++, it could be COBOL, it could be C#, takes that front end source language and turns it into some intermediate form. Right? So it does the first half of the job. It takes care of the language specific stuff and ends up with a form that's ready to hand off to the second part of any compiler called the backend.
Okay.
The backend takes that input and it does huge amounts of analysis on it and generates both code for the actual platform you're going to run on. That could be Pentium or Itanium or 64-bit versions of chips and so on. And it usually performs lots and lots of optimizations so that the resulting code is either small or runs faster than just code that was generated without optimizations.
So the front end, what does the front end yield? Right, it's not yielding machine code that then passes to the back end, because that would be kind of a complex interpretation. So what does it produce to hand off to the back end?
So in the case of Microsoft, there's two varieties. If we look at managed languages like C#, J#, Visual Basic and so on, they produce an intermediate form which is called an assembly. And it contains two things essentially. It contains MSIL, that's Microsoft Intermediate Language, together with data structures which we call metadata. So for all these managed languages, that's what it produces.
Okay.
And it's the same for other languages that people have written that target the .NET framework. So COBOL, IFO, the list goes on and on. So that's one species, they target managed assemblies. The other one is the native C++ compiler inside Microsoft, and that produces an intermediate form which, well, it doesn't matter what it's called, it's just an intermediate form that is fed directly into the back end. And as I was saying earlier, Phoenix essentially concentrates on the back end as opposed to the front end.
Okay.
So if you want to do lots of optimization or extensive analysis of software, then Phoenix is the framework that helps you do that.
Outstanding. Now, if you already have an existing application written in C++ that was compiled using the traditional non-Phoenix backend compiler, right, and you wanted to do more optimizations, how would you do it? Like, how would I utilize Phoenix to say, I want to take the backend out from the compiler that I use and throw in my own? So is it basically, can you extend an existing compiler that's built on the platform, or?
Right, so in fact that breakdown, just concentrating on native C++ today, the front-end compiler is called C1, that was the original C compiler, or C1XX for the C++ front-end. And they exist today, and that's what's used to compile current C++ programs. The back-end is called C2. And today's technology, which has been going for maybe 10 years or so, has this component called C2, and that does the heavyweight optimizations. Today in Phoenix we have the Phoenix version of C2, and we can simply replace today's C2 product with the Phoenix version and run the optimizations through there, yielding results from Phoenix.
Okay.
So that's a whole-scale replacement of one backend by the new technology backend of Phoenix.
Fantastic.
But you can do it at a finer level of granularity as well. So if you, for example, are a vendor who has a specific need for doing specific optimizations in your kind of software, it would be good if you could write your own compiler backend and optimize just for your special case. But building an optimizing backend, that's a huge job. That's dozens and dozens of man-years of effort, as we're finding in Phoenix. But what if the backend itself is composed of many phases, different optimization phases? Today we've got, I think it's maybe 25, maybe 30. Okay. It's also possible with Phoenix to remove one of these optimization phases and plug in your own one. You don't need to have access to the Phoenix sources. You just provide a DLL that has the phase you want to replace. You run it, you specify your plug-in DLL, and that's what happens. It replaces the existing phase that you've named and does the extra special optimizations that you're interested in for your case.
So now, is this, you're calling it Phoenix, so I'm assuming that's the code name. Is it readily usable today? Like,
So today, as you say, I should point out, Phoenix is a code name. We don't know what it will be called when it eventually ships, but today it's called Phoenix. And current status is that in fact we have a version which we call the RDK, which stands for the Research Development Kit. We've been shipping that, we're on about our 4th one now. We ship it every 6 months with new updates.
Okay.
We make that available for academic use, both research and teaching. So as I say, that's been shipping for coming on a couple of years. That's available for free download from our website.
Okay.
So folks outside can download that, experiment, play around, put in new plugins, etc.
Excellent. So yeah, we will definitely link to that on Channel 9. So as part of this, we should can we dig into how it works? Can we dig into how you, basically sounds to me like you've made a modularized sort of back-end platform infrastructure. How do you guys pull it off? You know, how's it architected? That kind of stuff would be very interesting.
Would it be useful to scribble something?
Totally. Always useful to scribble on the whiteboard. That down. Right.
Okay, so I'll just scribble what I talked about earlier, which is the case where we have a source program and that might be written in C# or Visual Basic or J# or whatever, a managed language. That runs through the front-end compiler and produces there a .NET assembly file. Alternatively, specifically for the case of native C++, that runs through a front-end compiler and produces some intermediate form. It's called CIL, but let's not bother about the details. Then Phoenix enters the picture back here. So the Phoenix framework can accept either that input or import that input. And it starts by converting it into an intermediate form which is specific to Phoenix. So it converts the input into a certain form using a thing called IR, intermediate representation. And eventually out the back it will produce native code. Okay.
Okay.
Now, as you know, because the way that managed code works, it's usually JIT compiled. In other words, it's compiled from .NET assembly language down into native code just at the last second,
Sure.
milliseconds before you require it to run. So that would be done as a just-in-time compilation. Whereas this conventional native C++ all the way down to native code is done as a batch mode.
Hmm.
And Phoenix supports both of these.
Excellent.
Other things to point out. Phoenix, as I showed there, can import a .NET assembly and then do either optimizations or software analysis on that. We also support doing things like having got into intermediate representation there, IR. That will then run down through a long pipeline of analysis and optimizations. Eventually going down to code generation, that's converting from IR into the native code for the target platform, and then emission. Okay. So as well as doing the straightforward, suck in some source language and then emit native code, you can also use Phoenix for doing analysis or code injection. So you might, for example, have a .NET assembly that you want to analyze and then inject extra code into it. So if, for example, you wanted to do tracing calls that traced every routine before it was called and just after it returned, you could run that into Phoenix, analyze the IR, inject extra instructions, and then instead of emitting it all the way to native code, just instead turn it back around and produce an instrumented .NET assembly.
Wow.
Okay. As well as doing that for .NET assemblies, we can do that for native code too. So
Okay.
we can suck native code in, so that might be a .exe or a DLL. We can read that in, analyze it, and either just produce analyses or extra optimizations after the fact, or code injection, and so on.
So then theoretically, you could add some sort of static analysis security tool into your Phoenix backend that then analyzes for potential buffer overflows, and then finds them, changes them, or marks them somehow, or I don't know. Can it actually change? Well, it optimizes code, so clearly it can change code, and then returns it back to you and says, "Here's a version that isn't as buggy as the one that you just tried to compile."
That's right. So, for example, one of the groups that we're working with is the group from Enterprise Development Tools. There's a package which is called Prefast, which now ships and is, I think it's /analyze is the switch that's used to enable that. But that will analyze a C++ program looking for problems in it. And it does a good job today. The Prefast team are currently using Phoenix to prototype more advanced analyses. For example, taking the source and checking whether there's any variables which are not initialized before use. So that team, as I say, is using Phoenix at the moment to experiment and prototype, future releases of that product.
Fantastic. So now this has, though, when you say platform, does that implies to me anyway, as a developer way up on this, way over here, that there's some sort of API?
Oh yes.
Okay, so what is that all about?
So everything that sits inside Phoenix, or more or less everything that sits inside Phoenix, in a fairly large DLL called Phoenix.dll, has APIs which allow programmers to manipulate any of the information contained in there. So as one extreme example, let me simply switch to a new colour. So as one example, I mentioned earlier plugins. That's where a given piece of code, either native or managed, is being compiled through the Phoenix framework. You may, as a vendor or a developer, decide that that particular block there, for example, that could be one of the optimizations like register allocation. You may decide that you can do a better job than we can in Phoenix for whatever reason. With a plugin, you have the flexibility to supply your own DLL. For example, my register allocator. And that will replace or change the behavior or in some way augment the existing phase inside Phoenix. All of that behavior is controlled by APIs, and in fact the minimum plugin that you can build requires about 15 lines of code. And
15?
Yeah.
Wow.
The plugins are managed because Phoenix.dll is managed as well.
It is. So you said it's managed.
Yeah. So let me take a step back.
Sure,
in fact,
please do.
It's both.
Okay.
So Phoenix itself is written in C++,
Okay.
and that allows us to build Phoenix.dll as either a managed binary or native. So we take the same source code and by throwing a switch, compile it all native or compile it all managed. For the most part, we're concentrating on the managed version, and that, for example, is the version for which we support plugins, user plugins.
Now, why was that decision made?
In terms of dual mode?
Yeah, in terms of only supporting managed plugins.
Essentially because the managed environment developing for .NET Platform is a whole lot easier to do than developing for native.
Okay.
You don't have the problems of memory leaks and allocations and freeze, etc. So all of that is taken care of for you, and you can write plugins, minimal plugins for there, as I say, starting at 15 lines of code and building up to be as complex as required.
Okay. But so if I have a really complex DLL that I want to insert into my backend, I have to write it in a managed language.
Today, that's the
that's
mode
the
that we
case.
support, and that will probably continue.
Sure. So that way you can't end up building a memory leak or something bad into the backend compiler,
That's
messing
right.
up the playing field.
That's right. It's a fairly difficult job to write a back-end optimizing compiler, as you can imagine. So the easier that we can make it for anyone to add code that works correctly, that's the way we'll go. And managed is significantly easier than native.
Yeah, I mean that's pretty interesting when you think about that. Think about the implications of that.
Yeah, I think as well that another point to mention is that I've talked about the APIs to support plugins there, but in fact almost all of Phoenix is available through APIs. So for example, if you have written code and you want to perform, analyze the control flow graph, that's one call and it's done. If you want to build the data flow graph or SSA form, again it's one call and it's all done for you. It takes care of the heavy lifting rather than have to spend several months yourself writing all these algorithms.
That's excellent. So how long you guys have spent about? You mentioned like 12 years on this, or
About 4.
About 4 years.
So the original back-end compiler dates back about, I think it's around about 10 years. We've been working on Phoenix for about 4 now.
Okay.
It started off as a joint project with MSR here in Redmond, with the intention of capitalise upon the good research that's been going on inside MSR on tools and languages, as well as develop a common framework between product teams and research. Because if we've got the same underlying framework on which to both build product and experiment, the aim is that it will ease the migration of ideas from MSR into product in the future.
Outstanding. That makes very good sense. And as we had talked about earlier, the tools, many of the tools that are being created for code analysis are coming out of research. So
That's true.
it's a natural kind of marriage of...
Yeah, when you start thinking about what you might use Phoenix for, there's dozens upon dozens of applications.
So for example, once you go inside a .NET assembly, you might want to instrument it, you want to analyze it, you might want to morph it by putting in features that are not supported in IO assemblies. So for example, work done on a prototype investigated introducing bitfield instructions into .NET assemblies. The bitfield instructions do not exist in the .NET framework, but you can morph the assembly in such a way that you can compact, instead of having, for example, 100 separate Boolean fields, each of which contain, use up a whole byte. You could compress that down into individual bit fields and then morph the assembly so that at runtime the instructions are available for instead faking up the original behavior but now using bit fields instead of entire bytes each.
And how do you get around the fact that you're running in the framework context? How do you morph? I realize that in the end, the .NET assembly, like everything else, turns into just machine code. And so what you're saying is you're morphing it post-IL, so you don't have to deal with the JIT complaining.
That's right.
So you're doing a post-JIT morph.
Yes.
In your back end.
So
how does that work?
We're doing a morph on the .NET assembly itself.
Okay, so that you'd be at this level.
Yes.
And so you do the morph in your Phoenix compiler.
And emit a modified .NET assembly.
And you modify .NET, but with modified IL.
With modified IL.
That's
right.
legal.
And modified, yes, and modified metadata. The two must match, obviously.
Okay.
And there's other things you can do too. So, for example, if you're interested in obfuscation, again, once it's converted into Phoenix IR, you've got a large framework on which to do analysis and modification of the IR. And again, there's research efforts going on in that particular area too. Or we had an intern last year who developed a system using Phoenix that supports aspect-oriented programming. So you build the aspects that you want woven into the assembly, and you use Phoenix to do that weaving.
Interesting.
It turned out a very successful intern project.
So now, can you take? So if someone else wrote the assembly, you'd have to first inspect it with some tool, and then figure out how you want to morph it. So if someone so this intern was probably not given an assembly written by someone else, and was told to weave aspect oriented programming into it, right?
So AOP is a general framework, so that, for example, if you wanted to inject using AOP a logging mechanism to just say which routines were called, you can do that for any assembly whatsoever with one standard approach. So I've forgotten whether he experimented on an assembly that he wrote himself, or maybe just a system one that he picked up. I've forgotten. But the approach applies to both.
Fantastic. So where do you think Phoenix is going? Like where is it going to be when you ship?
So at the moment we're heads down, working very hard using agile development with scrums and monthly sprints. We've got about 6 teams working on that. We're on sprint number 5, finishes Wednesday in fact.
Wow.
We have a total now, it built up slowly, we've not had this number of people on it for all 4 years, but in the last 6 to 9 months we've built up the team. We now have about 30 developers on Phoenix.
Nice.
The focus is to build Phoenix to the point where we can take the whole of the Windows operating system, all 50 million lines, build it using Phoenix, and then boot the system up. And in fact we can do that today with Phoenix. Where we're heading next is doing that same thing, but now turning on more and more optimizations within Phoenix.
Interesting.
So that's one focus, and the other one is to provide JIT compilers for 64-bit built using Phoenix.
Okay. Very interesting. So wow, I mean that's amazing to think of compiling Windows with your new backend.
That's quite a high bar to reach. And And it's taken a while to get there, but we can build, boot, and run
Now-
Windows today.
Do backends, because when I think about that, would Phoenix have the capability, or backend in general, does it have any notion or concept of dependencies between calls? So if you hand over this DLL, or for example Windows, which is a collection of God knows how many DLLs and all this other stuff, or just source code, and then you compile it and figure all that out. Can you do dependency mapping in the back end?
Well, see, so if you wanted to do dependency analysis and find out a better way to factor all the hundreds of DLLs that currently make up a large product, yeah, you could use Phoenix for that.
Excellent.
You would need a fair amount of memory, obviously, because the technique that you're using there is similar to one called whole program analysis, wherein rather than just build and optimize one DLL at a time, you suck in lots of DLLs, well, the sources, the intermediate rep for lots of DLLs, and do a global analysis across all of them and produce the optimized code for that case. So dependency analysis, yes, for sure.
Very interesting. And then, as we talked about earlier, security is a big one.
Yep.
For your code security.
Again, we have partner teams within Microsoft on campus here experimenting with Phoenix for security investigations, trying to find those difficult bugs that could lead to a security hole.
So now, when we talked about JIT earlier, you drew it in Phoenix. Is that where it is?
Yeah.
Where does the JIT compiler live in this world?
So the JIT compiler is, in a way, just another compiler, like a batch compiler, except it runs just before the code is required. It uses a fair amount of the Phoenix libraries. I think one number I remember from a few months back, if you look at the C2 optimizing backend, the C2 compiler itself is only a few thousand lines of code because it makes use of all the features provided by Phoenix. In the same way, if we looked at a JIT compiler, it would be, I don't know the number offhand, but a few thousands to maybe a few tens of thousand lines of code, but again, using the optimization framework inside Phoenix.
Excellent.
At the moment, that's the difference, that JITs today are native. They have to be native unmanaged code. So that is a case where we ourselves make use of the native built version of Phoenix.
Interesting. And so if you wanted to optimize the JIT, you're pretty much out of luck using Phoenix. Today. I mean, you wouldn't want to.
In terms of plugins, yes.
Yeah.
I thought you meant, so you can view it, there's a kind of cycle going on there today that we have a JIT that is built using today's compiler. You could run that through the Phoenix version of C2 and produce an improved JIT, which itself uses Phoenix to produce better optimized code for the original sources.
But you still need to be an engineer with the, pretty highly skilled and understanding what optimizations you would need to provide. Like, you know what I mean?
That's right. If you want to produce a plugin for the managed Phoenix C2 backend compiler today, then simple plugins are fairly simple. As I say, you can write simple ones in a few dozen lines of code. If you want to replace a given optimization phase, you really need to understand the details of backend compiler optimizations, which is a large field that's been established and people have been researching it for decades, literally. So it's not an easy area to drop into, but it's possible.
Sure.
Whereas before, a compiler that you bought was just closed, sealed box that you had no way of influencing its behaviour, except from the command line switches that you provided. With Phoenix, you can modify its behaviour.
Now you can. So with Phoenix, you've made compilers programmable. Backend compilers are now programmable.
That's right. Instead of just sealed black boxes,
Yeah.
you can change their behaviour.
That's really very, very interesting, and makes sense why you went with academia and research first to get your feedback. 'Cause
Yeah.
That's so. What's the response been? What's the feedback like from, say, academia?
So for academia, we've been shipping the RDK for some time. I think the last time I checked, the previous version had got about 200 downloads worldwide.
Okay.
It's been well received. We've had a handful of papers published based on research using Phoenix. We've also we're into our second year now of an RFP process, and we awarded about a dozen research grants to various universities, again to conduct research using Phoenix.
Excellent.
So some really interesting work coming back in.
I bet. Well, that really is fascinating. I mean, theoretically, this might be sort of off the wall, but and it totally is off the wall. I was thinking about how you could use Phoenix to generate platform-independent machine code
Yes.
from your .NET sources.
Right. So another aspect I've not mentioned is at the back end there, when we produce native code, I've talked most of the time about as if it were only x86 native code for Pentium. In fact, we have versions that target Itanium and x64 as well. The good bit about that is that all of the the bulk of the optimizations are independent of the actual chip for which you target. So if, for example, you wanted to build a back-end optimizing compiler for a new chip, ARM or PowerPC or whatever, most of the code you would need to build is already there, all the optimization phases. What you need to do is change the very back end of the back end to emit different native code. The target there is that we should be able to get something up and running for a new chip in about 3 months development effort. And then, with about another 3 months development effort, be able to enable all the optimizations that Phoenix provides and emit good, robust code for that new target. So I guess the obvious question is, well, that's a target, 3 months to do this, 3 months to do that, but do we believe it's really possible? So we had an intern a couple of years back who came over and retargeted the existing Phoenix compiler, but instead of emitting for Pentium or whatever, he emitted for ARM, the ARM chip. And he got the bulk of that running during the 3 months that he was with us during the summer. So we feel it's not far out in terms of, if that were an experienced compiler developer, he could probably get that up and running with good code quality in about 3 months.
Wow.
And that's a huge difference from today's situation, where without Phoenix, if we had to build a compiler for a new platform, it takes a long time. And we found that out in developing new JIT compilers for Itanium. We already had one for Pentium. To develop a new one for Itanium, that was what turned out to be a fairly massive investment. It took a long time to get that right.
And that's because of how the processors deal with, let's talk about that. Like, why is there such a dramatic difference between processors and in the end, what are you giving them? Right, you're giving them machine code. That's all our processors speak.
That's all they understand.
So where is the challenge? I can understand when you go from 64, 32 to 64, but let's talk about that for a moment.
So the aim is that Phoenix is a large amount of software, right? The aim is that the bulk of that is platform independent. So if, for example, you're sucking in a .NET assembly, then as much as maybe 80% of Phoenix code does the same sorts of optimization, no matter whether you're emitting for a Pentium or for an x64 box. It's only the very back end of the back end that you need to change to target different machine codes. Now, when you look at the details of different chip architectures, the machine code emitted can be vastly different. So Itanium is different from almost everything. And the code generation for that is particularly difficult to get first of all correct, but secondly optimized to make use of the multiple issue instructions that it supports.
Interesting. So, are there any challenges with multi-core chips?
Yes. So as we all know, the dream of Moore's law, where the speed of processors doubled every 18 months or so, has kind of come to an end. You know, the gigahertz rates have stopped going up. We're still around about 3-ish gigahertz, and have been for about a year now. So the free lunch is over. However, Moore's law in its precise form still holds good, in the sense that companies like Intel and AMD can still pile on more and more transistors per square millimeter, and that's still going up year by year. But rather than increasing the CPU speed, instead they're giving us more CPUs. So going into the future, what we want to do and what we're experimenting with is to build frameworks that can make use of that extra power. Initially by changing or adding to the programming language features, so that developers can make use of multi-core. Ideally, long term, being able to do that automatically by sophisticated analysis, so that you would take the original source program, which was written just like it was 5 years ago, but then auto-parallelize that source code in the back end.
Phoenix.
Yeah,
Exactly.
so that's the aim. Experiments, you know, in research so far has had limited success there. So it's not something we're going to solve this year or next year, but work is underway.
Yeah, I mean that's an excruciatingly complex problem.
Yes.
To take code that wasn't written in a concurrent fashion explicitly, and have to figure out statically in your Phoenix DLL how to re-optimize it such that things, you have to figure out basically what operations should be happening in parallel.
That's right.
And then target them at the right core, or however that architecture works. When you spit this out, yeah, that would be amazing.
Yeah.
That would be amazing.
In a way, there's a backend compiler does a whole pile of really sophisticated analysis already. So it analyzes data dependencies to know that, for example, this instruction and another instruction 3 later don't actually have any dependence between them. So they could be reordered, but still get correct answers. So it does that sort of analysis today in order to optimize. But we are certainly looking at a step beyond to make use of multi-core. Because if you think of multi-threaded programming, that's rocket science. That is really, really hard to get correct for experienced developers. And now we're talking about attempting to make a compiler get the correct answer, where experienced developers often make mistakes.
Sure.
So it's kind of hard.
It's kind of hard, but you know, the analogy I would draw is the class of developer that is building back-end compilers that do very complex analysis are similar to the class of developer that writes kernel for an operating system. Because kernel developers are well versed in multi-threaded programming, and they live and breathe locks, and they've gotten the art down. It really is an art, and they're artisans, and they've figured out how to do it incredibly complex. I mean, for example, Jim Gray is an example of somebody who loves locks, and won the Turing Award for some work he's done around really incredible concurrent code that was written in such a way using locks that it seemed. Anyway, the point is, but not everybody's a Jim Gray, and that's the point. And not everyone's a back-end compiler developer or a kernel developer.
Yeah.
So for the 90% of the rest of us, amen, it's very difficult for us to write predictable, reliable multi-threaded code because it's just hard to do. The platform doesn't really support it native.
That's right. It's just, as you say, it's very hard to get multi-thread code correct. But looking ahead, several years, when instead of having, all the chips will still be, I guess, around about 3 gigahertz, but instead of having one CPU when you buy your laptop, you might have 10.
Yeah.
And in that regime, you cannot expect everyone to become so expert at writing multi-thread code that they write all their applications that way.
Yeah.
Eventually it has to be handed down to the optimizing compiler to do that.
Absolutely. And that and or the system that's actually running the code
Yes.
could also play a role someday.
That's right.
Right. Well, that's very interesting. So let's talk. So we got a few more moments here, and this is Channel 9, and one of the things that we're interested in Channel 9 is also the people behind the products, right? So, you're a program manager in the C++ team. How long have you been here? Why Microsoft? How long have you been doing C++? That kind of stuff.
So I've been in Phoenix 2 years. Before that, I spent 5 years in the CLR team, just over the street in Building 42.
Okay.
Prior to that, I was a kernel developer for the VMS operating system with Digital.
Okay.
Why Microsoft? Because you get to work with fantastic developers. Work beside some really awesome developers, highly talented. And in this team, very experienced. There's guys working in this team who have been writing, optimizing compilers since they were knee-high, So they have like 15, 20 years experience in the field. And every day in conversations, you just learn so much.
Excellent. Cool. And so we will have the URL for Phoenix. We'll put it up on Channel 9 as part of the video post. And as you mentioned, though, you did say it's just for academic and research at this point, or can anybody download it?
So anyone can download
Okay.
it. It's unencumbered. It has no NDAs.
Okay.
Anyone can download it. The only condition is that you cannot then go on and ship it as a product. Okay. So you can experiment. You can use it for classes. You can teach. You can try things out. But you cannot ship Phoenix as part of your product.
Okay.
So that's the only constraint.
Understood. And that clearly won't always be the case, right?
Right.
Yeah. Otherwise,
going into the future, we'll be supporting it for commercial use. Initially, for a few close partners. So one of the things that I did not touch on was obviously, if as a third party you provide a plugin that modifies the behaviour of Microsoft's frontline C2 backend compiler, what guarantees do you have that the code emitted is still correct?
exactly.
So there's a whole pile of business issues around that says all plugins will fall into two camps. One, produced by whoever and no guarantees given. Others with whom we have entered a partnership and done joint testing and development, and these particular plugins will be certified somehow as officially blessed and having been extremely carefully tested.
I could see how that's going to be interesting, but we've pulled it off with drivers to some degree, so it can be done.
It can be done. It's business issues and a few technical issues, but technically fairly straightforward.
Especially because the way you designed it,
Yes.
by keeping everything managed
Yes,
for plug-in model.
that's right.
Really
Makes
helps
things a
you.
bit simpler. Yeah.
Totally. So I understand even better now why you would have done that. Excellent. Well, this is incredibly interesting. I look forward to finding out how Windows, how that goes. Now, we're talking about iterations of Windows. We're not talking about Vista, so it'll be the next snapshot of Windows will probably
right.
be compiled using Phoenix.
That's our sincere
the goal.
hope that we shall compile it and ship that product using a Phoenix-based compiler.
Outstanding, and which also means Office will eventually as well.
Eventually everything, yeah.
Eventually everything.
Yeah. In a way, it's a high bar to meet because we are competing with ourselves.
Sure.
We are competing with today's Visual 2005 C++ compiler, which is arguably one of the best on the planet. And we've honed that and optimized it and given it lots of tender loving care for about 10 years. So for Phoenix to come along and be successful, we need to beat ourselves and
Sure.
then go beyond that in terms of the code quality we eventually emit.
Fantastic.
So it's a high bar.
It's a high bar, but it seems like you're going to pull it off, and I'm sure there's a bit of that Visual 2005 backend compiler magic happening already in Phoenix, right?
Yep.
And you're sharing some constructs, I'd imagine.
That's right. We've got all of the expertise from the team that built that,
Exactly.
contributing towards Phoenix.
Fantastic. And now you've definitely upped the bar significantly by making it programmable. Very exciting stuff. And it's not just specific to unmanaged code. As you mentioned, the front end doesn't matter, right?
That's right.
Not really.
That's right. Although we're part of the C++ team organisationally,
Yeah.
we are delighted to compile anyone's code. We are happy to compile any language.
Sure. Fantastic. Well, thank you for your time, Jim.
Okay, thank you.
Appreciate it.
Cheers.